Okay, so I now want to solve the wave equation, the one-dimensional wave equation. If we have 0 here and g of x here, this board should look very similar to what it looked like in the first exam or the first video. I meant to do a first video where I had f there and g equals 0 there. And then I meant to do a second video just with the same exact board setup, but I had to teach my other class, and so I had to erase part of it. But it looks something like this. Okay, so in this setup here, all of this, solving the differential equation for the Fourier transform is going to stay the same. The only difference is we'll have a 0 here and a g hat of omega here. And if you solve this for a and b, what you're going to get is a of omega is equal to g hat of omega over 2I omega, and then b of omega is minus that. So b of omega is g hat of omega over 2I omega with a minus sign. And so overall what this tells us is u hat of omega t, and I'm going to write this in a very peculiar form, but there's a reason. It's going to be 1/2 times g hat of omega times e to the I omega t minus e to the minus I omega t divided by I omega. And again, I want to find the inverse Fourier transform. So I'm going to have u of xt. I'm going to do, you could do like convolution things, the convolution of g with the inverse Fourier transform of this, but I'm just going to look at the formula for the inverse Fourier transform. It's going to be 1/2 times 1 over the square root of 2 pi times the integral going from minus infinity to positive infinity, g hat of omega times this part right here, which is e to the I omega t minus e to the minus I omega t over I omega. I know I'm in the way, so I'll step out of the way in just a second. And then times e to the I omega x d omega. Okay, well, I'm looking at this part. I'm going to have to figure out what to do here. So I'm looking at this part right here, and I'm realizing, hold on a second, e to the I omega t over I omega is the antiderivative of e to the I omega t. If I think about this a little bit, this quantity right here, this is equal to 1/2 times g hat of omega, but then this quantity in the brackets right here is equal to the integral s going from minus t to plus t of e to the I omega s ds. The quantity in the brackets here is equal to this integral. Okay, that's going from minus t to t. The antiderivative here is e to the I omega, e to the I omega s over I omega, and we're evaluating it from minus t to t, which is exactly what we have here. So what I can do then is I can replace this bracketed part right here with this integral. It's the integral s going from minus t to t of e to the I omega s ds. Well, notice what I can do here. Even before worrying about changing the order of integration, I can write this as ds d omega, but now I can combine these two into one exponential. And so it's going to be e to the I omega x plus s. So it's e to the I omega times x plus s ds d omega. Okay, now what I'm going to do is I'm going to change the order of integration here. Okay, I'm going to change the order of integration. So let me go on ahead and bring this g hat of omega over here. And I'm going to have d omega ds. And now I'm just going to swap these integrals here. So this is going to be s going from minus t to t. This is going to be omega going from minus infinity to positive infinity, and I'm going to sneak this 1 over the square root of 2 pi. I don't know why I said sneak. That was weird. 1 over the square root of 2 pi like this. Well, what do I have here? If I look at the inside integral, this is the inverse Fourier transform of g hat evaluated at x plus s. So in other words, this inner integral here is just equal to g of x plus s. And so now I can write that. So this whole integral here is g of x plus s. ds with the 1/2. And so now my claim, all of this analysis says that this is a solution to this equation. X and t are the variables. Because I want to, and because it's sort of traditional, we don't want the x to show up there. We want the variables, the x and t variables, to just be there and there. There's nothing wrong with this. It's just typically how it's represented is the x variables are there and there. So I'm going to do a change of variables. Introduce a new variable. Tau is equal to x plus s. So if I change this integral over here, if s is equal to minus t and tau is x plus s, tau is going to be x minus s. X minus t. S is equal to minus t. So x plus minus t is going to be x minus t. And then up here is going to be 2x plus t. X plus s is equal to tau. And then ds is equal to d tau. If you do d tau, you get ds. So this is just d tau. Okay, and so my claim is that this function right here is a solution to this problem. So I'm basically going to erase everything and just write the solution up here. So up here we get that u of xt is equal to 1/2 times the integral tau equals x minus t to tau equals x plus t g of tau d tau. Okay, now I want to show that this satisfies the differential equation. So if you remember when we solved the other one, or similar to how we solved when we solved the other one, there's, in order to make this Fourier argument work, you need to have some assumptions on f and g. In particular, you can take the Fourier transform sort of naively and compute it naively with integrals. Well, this requires that f be absolutely integrable. Well, just and g be absolutely integrable. But this formula here does not require that f or g be absolutely integrable. This just requires that it's what's called locally integrable. In other words, on any finite domain, you can take its integral, which any continuous function satisfies, and any differentiable function, since that's also a continuous function, is also going to satisfy. Okay, so we have much less restrictions on g at this point than we did at the beginning. So this is another case where we sort of, our methods sort of indicate or impose these extra conditions on the initial data that our final solution does not impose. Okay, so now all we're going to need to know is that g is differentiable, or g is continuously differentiable, to show that this function satisfies this equation here. So it's like we use the Fourier transform method to give us a candidate solution, and then we say, oh yes, I'm going to verify that this actually does satisfy the solution by taking derivatives and stuff like that. And so that's what we're going to do now. All right, if I take the derivative of this with respect to t, actually, first let's show that it satisfies this boundary condition. If t is equal to 0, the integral goes from x to x, and an integral from one point to that same point is equal to 0, so it satisfies that condition. If I take the t derivative of u, okay, we just need to make sure that I do the chain rule properly here. It's going to be 1/2. Okay, so this is a fundamental theorem of calculus. If I take the derivative of this with respect to t, notice that my endpoints here contain t. So what does it say? It's going to be the integrand, or what does the fundamental theorem of calculus say? It says the derivative of this with respect to t is going to be the integrand evaluated at the top endpoint, so that's x plus t, times the derivative of x plus t with respect to t, which is just 1, and then minus the integrand, which is g, evaluated at the bottom point, which is x minus t, times the derivative of x minus t with respect to t, which is minus 1, so it's going to make that plus. Okay, now here, notice if you plug in t is equal to 0, you get 1/2 g of x plus g of x, which is equal to g, and so this does satisfy that other initial condition. And so, yes, this is satisfied. Okay, but now I'm still in the middle of checking whether or not it satisfies the PDE. If I take a second derivative, now I just do the normal chain rule, or the normal multi-dimensional chain or multivariable chain rule. It's going to be g prime of x plus t times the derivative of x plus t with respect to t, and that's 1, plus g prime of x minus t times the derivative of x minus t with respect to t, and that's minus 1. So we're going to have this. Okay, so that's the double t derivative. Okay, so now let's do the double x derivative. It'll give us another chance to do this chain rule. So it's going to be equal to 1/2 times, okay, I'm doing the derivative of this with respect to x. It's going to be the integrand. This is the fundamental theorem of calculus, or the Leibniz integral formula, whatever you want to call it. It's going to be g of the top limit, which is x plus t, times the derivative of x plus t with respect to x, which is just 1, minus g of the bottom limit, that is x minus t, times the derivative of x minus t with respect to x, which is just 1. And then when I do a second derivative, okay, just do the normal multi-variable chain rule over here. It's going to be g prime of x minus t with respect to t times the derivative of x plus t with respect to x, minus g prime of x minus t times the derivative of x minus t with respect to x, which again is just 1. And so if you look at these two formulas, they are definitely equal to each other. And so yes, this function now we have shown that it satisfies this PDE as well, so it satisfies the whole problem. Okay, so then overall, and let me just point out again, unlike the diffusion equation, the wave equation does not give us any more regularity than what we started with. Okay, we don't automatically get an infinitely smooth solution, and in general, this is what's going to happen. Okay, so these are two very different behaviors that you get in the solutions to the diffusion equation and solutions to the wave equation, and it very much that is a huge, a very big important point in the analysis of these different equations. All right, so then overall, the solution to this overall equation is u of x plus t is equal to f of x plus t plus f of x minus t over 2 plus 1/2 times the integral tau equals x minus t to x plus t g of tau d tau. That is the solution to this overall problem here. This satisfies the linear PDE with f here and 0 there. This satisfies the linear PDE with 0 here and g there. So their sum satisfies the boundary conditions. Since the PDE is linear, a sum of solutions is itself a solution. But that's only because the PDE is linear. Okay, that is it for this video, and I believe this is my last video for the week. Next week, we're going to start looking at properties of these solutions. Okay, that's all.